Hey gang, just wanted to make a quick video to help you read the material for chapter 32. So this is kind of a half reading guide. I want to walk through some of the things in sections 32.1, 2, and 3, which are all we're going to cover from chapter 32. So 32.4 and 32.5 are now optional. Briefly in 32.1, these are just some basics of what is electromagnetic radiation, which we gave some hints about last time. These all follow from Maxwell's equations. Our two Gauss's law, Faraday's law, and Ampere's law with Maxwell's correction about displacement current. So these four show that changing magnetic fields are going to produce electric fields, and then changing electric fields produce magnetic fields. And so we get a feedback, and this creates electromagnetic radiation, which will travel through empty space at a constant and unchanging speed. So those are some of the things we're going to find today. So just a little bit about the result before we get to the derivation. Sorry about Hazel there. We're working together on this video. So one of the first things about how to get electromagnetic radiation is that this is going to come whenever we accelerate charged particles. So moving charged particles will create B fields, stationary charged particles create electric fields, but when we accelerate them, speed them up, slow them down, wiggle back and forth, or change direction, then this is going to produce electromagnetic radiation. So here we see this pattern. You can imagine this Q moving up and down and creating a ripple in the electric field. So here we have this changing at different times. So if you look over here, the electric field's up. A little while later, it starts going down, etc., etc., as this particle moves. This is obviously a pretty complicated pattern. So what we're going to actually consider is a different setup. But first, a little bit about the result. We find that through combining Maxwell's equations, we get a speed of light of 3 times 10 to the 8th meters per second. And this is the speed of light in vacuum, which is constant and unchanging. Electromagnetic radiation is a wave, and therefore is governed by this, looks like all waves, they have wavelength and frequency, and the speed of the wave is the product of the wavelength and frequency. So all magnetic radiation in vacuum travels at speed c, but it can have different lambda and f. So as the frequency gets bigger in our electromagnetic spectrum going this way, then that's getting smaller and smaller wavelength. So here we can see all the different types of electromagnetic radiation, or several of them. The visible light, which is actually a blow-up. All of the visible light which your eyes can detect is just in this little tiny sliver of this huge spectrum. The Roy G. Biv, red, orange, green, blue, indigo, violet, all hiding inside of there. Those are at about 10 to the 14th hertz, and about anywhere from 400 to 700-ish nanometers, so 10 to the minus 6 meters. So below that, at shorter, at smaller frequencies and therefore longer wavelengths, are the infrared, below red, infrared, and then microwave, and then radio. And then above the violet, as you go to higher frequency and thus shorter wavelengths, you get into UV, X-ray, and then eventually gamma rays. So I think those different types, you should be able to pick out the correct order: radio, microwave, infrared, Roy G. Biv, UV, X-ray, gamma ray. I think that's a good little piece for this chapter. Let's talk about finding how that c, that speed of light from Maxwell's equations. To do that, I think we could start with a pattern like this. Move a charged particle and ask, how long after we move it does this change in magnetic or an electric field occur some distance away? If we knew the distance and the time it took for that change to get there, then we could find it out. Clearly here this is a pretty complicated electric field, so instead our authors have asked us to imagine a much easier to picture change. Something has happened. Some charges over here, I don't know what pattern it is, it doesn't matter, have moved, right, have accelerated, and what that's done is create a planar wavefront. Can you imagine this gray square moving in the x direction at speed c, and we're going to find that out. So, behind that wave is a constant, or behind the plane, I'm sorry, is a constant upward electric field anywhere in space, and a constant B field here in the plus z direction. Out in front of the wave, there's nothing. It hasn't gotten here yet. So what we're going to do is ask how fast it goes in order to make this, and that's going to be our speed of light. So to get at that, we're going to apply Faraday's law and Ampere's law to this situation. And so to do Faraday's law, we need to do a path integral around some loop and ask how much the electric field's in that loop, and then we're going to ask how much the B field, the flux, changes that goes through that loop. So you can see here are, like, as time goes by, the wavefront's moving this way. So here's our most recent one. And any little small amount of time dt, that wavefront is going to move some distance, the speed of the wave times the time increment. Okay, so we're going to draw a little Amperian, or I guess a Faraday's loop, I don't know what to call it, a little loop, and track what happens to E dot dl as we go around it. Here in this part of the path that goes from H to G, that path is in the same direction as the electric field, so we get just an E times the length, which is A. As we go from G to F, our path is perpendicular to the electric field, so we get no addition to our path integral. Down here, when we go down from F to E, we're in front of the wave at this point. You see how that gray indicates we're out front here. So there is no electric field, so the product's zero there. And then on the return trip, E to H, again, where E and path are perpendicular. So the total path integral all the way around is minus EA. Next, we need to find the magnetic flux, the change in magnetic flux. So if you can imagine, this plane has moved in some little bit of time, dt, from here to here, from this position to this position. All right. So at the beginning of that time, the flux was this little piece of area, GH, bounded to this side, and then after it's moved and some little time dt later, it's now this bigger area. So the difference between the final and the initial is just this purple shaded area, which has a length of c dt and a height of a, and so the area is a c dt, and so the flux is the product of area and time. So when you divide the dt out, you get the change in flux of BAC. So you plug those two into to Faraday's law, and A, that imaginary, the width of this imaginary shape we've put in here, cancels out. From that A and this A cancel out when we set these two equal to each other, and we get that there is some definite relationship between the strength of the electric field and the strength of the magnetic field, and the constant proportionality is just the speed of light. So this is a pretty great piece of information. The problem is it doesn't quite solve for C. We don't necessarily know what the relative strengths of E and B are, whatever we had to do to turn on these two fields. So we need to go one step further, and that is going to be to, instead of applying Faraday's law, we're going to apply Ampere's law. Ampere's law tells us what happens as we walk around a path and see the B field in the direction of the path, and that's proportional to the electric flux. So to apply this, we need to turn our little Amperian loop on its side so that now the electric field goes up and through this surface, and we get a flux there. Again, as we walk around this path from G to H, we get that the B field and the path are in the same direction, so we get that term BA. On this leg and that leg, the B and the path are perpendicular, so it gives no contribution. And out here in front of the wave, there is no B field. So therefore, the total is just BA. So now we have to ask what's the change in flux, and again, in some amount of time, the wave front moves from here to there, and so the old area is there, the new area is the whole thing, and the difference, the change in flux, is just this piece here, which has area C dt A, and then so therefore flux is E times C dt A. and the change in flux then cancels that dt out, and we just get this piece. So inserting those two pieces into Ampere's law, we get another relationship between the strength of the B field and E field. This time they're not just related by C, but also by our two constants, the permittivity of free space epsilon naught and the permeability of free space mu naught. If we take this equation and combine it with the one we got from Faraday's law, this equation, plug one into the other, then E and B both cancel out, and we're left with a relationship between C, the speed of light in vacuum, and epsilon naught and mu naught, those two constants that we said were empirically found in Coulomb's law and in the Biot-Savart law. So this is a pretty neat moment that here we have electricity, magnetism, and light all related in one formula. So if we plug in our values for epsilon naught and mu naught, we get the speed of light around 3 times 10 to the 8th meters per second. All right, so this leaves us with some key results from that derivation. The first is that the electric and magnetic wave fields are transverse waves. All right, always E and B are going to be found 90 degrees to each other, and they're going to be 90 degrees to the direction of travel. So this little diagram is showing you how to do a right-hand rule. If you ever know the direction of E and B, then you can tell the direction of travel. Point your whole arm in the direction of E, roll your wrist until you can flap your fingers in the direction of B, and then your thumb will be pointing in the direction of propagation. There's also, if you the magnitudes of the E and B fields are related by the speed of light. So if you know the magnitude of E, you can tell the magnitude of B. That speed of light, C, is a constant and unchanging speed as long as you're in vacuum. This is the universal speed limit we've said before. We haven't really said why it's the universal speed limit, but we have found that it is unchanging. And then finally, this fourth point I think is interesting, that the electromagnetic waves are different from all the other waves we've dealt with before, like sound or water wave or a wave on a string. All of those waves were due to particles inside of the medium bumping into each other or pulling on each other, and that was moving the energy down. But an electromagnetic wave requires no medium. It will propagate through empty vacuum. All right, so down here at this part of the chapter, there's this derivation using the wave equation, a really important equation in physics and math, but we won't use it in class this semester. So you can skip there from page 1057 to 1059, and we're going to cover this sinusoidal electromagnetic waves. As you can imagine, any kind of a shaking of this charged particle in the middle is going to create electromagnetic waves, but we're going to stick with a sinusoidal. We'll shake this up and down like a sine wave. It turns out, we've mentioned this before, that you can actually answer questions about any kind of oscillation if you know how the sines and cosines act. So let's pitch that. So if we take this charged particle and give it a shake, then we're going to get an electric and magnetic field that are varying sinusoidally. So these two boxes I want to spend a little bit of time thinking about and how they relate to this picture. So here you can see that the electric field is always up and down. It's in the y-x-axis or y-x plane, and the B field is always perpendicular to it in the z-x plane. All right? You can check with your cross product that E cross B is plus x, so these waves are traveling in the plus x direction. So you can see that the electric field is a vector. It depends on position, distance along the x-axis, clearly. As you move along this direction, the electric field is changing like a sine or cosine. The electric field has a direction. It's in the j-hat direction. So for this plane wave here, that's the case. It has a magnitude, this E max. That's what it's going back and forth between. And then it has this sinusoidal piece. Notice that in the sine is the as a term that depends on position and a term that depends on time. So we saw how as you move around in space, the electric field changes. But if we take a look at this GIF, you can see that if that's kind of a static image, if you push play on that, you can see that as time goes by, the electric field changes as well. So here, if you look, if you just set at this one point, you would see that the electric field at your one position is changing as time goes by, same as the B field. You can also check that at this spot that E up and B out is a cross product that goes this way, but also at this point now, E down and B into the page is also a cross product in the plus X direction. So that's so this is kind of what the electric field looks like in slow motion. Obviously, these typically change a lot faster than this. There's also two kind of neat parameters you can see here. One is if you took a stopwatch out and timed from now until now, that would be the period, the time it takes for the electric field to go through one oscillation. So that's big T we usually use. And then there also, you can see in this graph, there's a wavelength, the distance from this peak to that peak, right? That's also the distance from this peak to this peak. So that the wavelength and the period are really the two parameters you can see in this graph, or time in this graph, and they're related to the terms in our cosine and sine piece. Also, those two are related to the velocity. Notice that the time it takes for the electric field to go all the way back up and down is also the time it takes for this peak to move one wavelength. So the speed of this wave is given by the wavelength, the distance it travels, divided by the period, the time that it travels. So if we go back to our book, we can see that that's represented here. If we want this wave to go to get back to where it started in one wavelength, then we need k to be 2 pi over the wavelength. That way, when x goes up by lambda, this term will have gone up by 2 pi and we'll be right back to where we started. Similarly, we have the same definition, omega, the angular frequency that we've always had. Omega is 2 pi over period. And that way, when t goes up by the period, then this term has gone around by 2 pi, and this cosine has just gone through one oscillation. So, but because k is related to omega, or lambda, the wavelength, and omega is related to t, the period, there is, and the wavelength and the period are related, that means omega and k are related. So not only is the velocity equal to wavelength divided by period, but it's also equal to the wave, the angular frequency, omega, divided by the wave number k. Notice that this is a wave that's traveling in the x direction. We can tell that because their x is the variable inside of here. We can also see that this is moving in the positive x direction. That's given by the minus sign here. Notice that the sinusoidal piece of this wave, the E and B, will always be the same. The magnitudes will be different, but we know the relationship between the magnitudes is proportional to the speed of light. And the direction that these two, the electric and magnetic field, are moving in also depends on which way it's going, which you can find by looking at the x and by looking at the minus sign. So the minus sign tells you that the wave is going the plus x direction because as time gets bigger, t goes up. In order for this thing to stay the same, you would need for x to go up. So this is as time goes up, this wave moves in the positive direction. Again, the amplitudes Emax and Bmax are related. The plus x is equal to j cross k hat. J hat cross k hat is plus x, so there's a relationship between those. We've mentioned that k and omega are related to the speed, and so therefore a common question you'll see in your homework and probably on the test is I'm going to give you some parts of one of these two, and then you can fill in the blank for the other side. You could find the direction because you know the cross product. You can find the magnitudes through this relationship, and we know that k, omega, and the speed are all related. Also, you can find lambda and period. So lastly, for this section, I'd like to discuss electromagnetic waves not in a vacuum, just in matter. So just briefly, if we're going to go into some other medium, light still propagates in some materials, dielectrics usually, and like glass and plastic and water. So if we're inside of a material, then the light is going to travel at some other speed, not c. So we've replaced that c with a v here in the two formulas that came from Faraday's law and Ampere's law. We've also had to replace epsilon naught with epsilon, the relative permittivity, and mu, the relative permeability. These are the permittivity and permeability of that material that the light's traveling in. So if we solve these two, we get that the speed in a dielectric is equal to 1 over the square root of the permittivity and permeability of the material. Well, if you remember that we had a relationship for the permittivity was the dielectric constant, K, times the permittivity of free space. So we've expanded epsilon to epsilon naught K and mu to mu naught Km. And this piece is just our speed of light again, and so we now have this new factor in the denominator. So the speed of waves in a vacuum is related to the speed in, the speed in a material is related to the speed in a vacuum divided by some constant. Turns out this relative permeability is almost always clearly close to 1 in materials that light can travel. So we can just kind of throw that out and let square root of k be pretty much equal to the square root of k times kn. And then we get a pretty nice formula here. If we rename the square root of the dielectric constant n, which is called the index of refraction. And this is the ratio of the speed of light in vacuum to the speed of light in that material. So different materials have different index of refraction. For water, it's about 1.3. For glass, it's about 1.5. N is always greater than 1 because the fastest light can ever go is when it's in vacuum. So N is always bigger than 1, and you're always dividing a large number by a small number here. Okay, so that wraps it up. Hazel's telling me it's time to wrap this video up. I think if you work through the examples in this chapter and give a try to that homework, you should be ready. On Monday, we'll review everything we did here and be really explicit about what's going to be on the test. But I think that the homework problems will be our guide there, and I think you should have, after this video, everything you need to do them. All right, thanks, and see you Monday.